Okay, thank you for introduction. Hello, I'm Jisung Park, a senior researcher and lecturer at ETH Zürich. Today, I'm going to present our work, DeepSketch, a new machine learning-based reference search technique for post-deduplication delta compression. I'd like to start with a high-level summary of this work. This work focuses on data reduction in storage systems, an effective approach at reducing the management cost of a data center by reducing the amount of data physically returned to storage devices. Among many data reduction techniques, post-deduplication delta compression can maximize the data reduction ratio by performing delta compression along with the traditional deduplication and lossless compression. However, we found that existing techniques provide significantly low benefits compared to the optimal because of their limited accuracy of reference search for data compression. In short, the existing technique often fail to identify any reference block for many incoming blocks that can actually benefit from data compression. To address this, we propose DeepSketch, the first machine learning-based reference search technique to generate a given data block's signature called sketch, such that the higher the data compression benefit, delta compression benefit of two data blocks, the more similar the two blocks' sketch values. Our evaluation shows that DeepSketch significantly reduces the amount of written data compared to the state-of-the-art baseline. Here is the outline of my talk, and I'm going to start with a brief background on data reduction in storage systems. In this big data era, modern computing systems deal with unprecedented amounts of data. For example, it is known that Facebook generates more than 4 petabytes of new data every day. So data reduction is an effective approach to reduce the management cost of a data center by reducing the amount of written data to storage devices, which in turn enables the system to deal with the same amount of data with fewer or smaller hardware resources. Post-deduplication delta compression combines the 3 different data reduction approaches to maximize the data reduction ratio. It performs a deduplication, delta compression, and lossless compression in order, and is known to be able to achieve more than 2x data reduction over a simple combination of deduplication and lossless compression. Let me quickly explain how post-deduplication delta compression handles the incoming write requests. Suppose that the system has an intermediate layer between the file system and the storage device, which we call a data reduction module. For an incoming write, the data reduction module first tries deduplication. If a write request has the same contents as a previously stored block, it skips writing of the requested data, but just maps the target logical block address to the identical block in order to serve future reads to the deduplicated block. If there is no identical data, the data reduction module tries delta compression. Here, block Y is slightly different from block B. So if the data reduction module somehow can find this out, it performs delta compression and stores the compressed data. In this example, the data reduction module also needs to keep the mapping information between blocks Y and B so that it can decompress the delta compressed data for future read to block Y. Finally, if there is neither an identical block nor a similar block, the data reduction module just performs a lossless compression. The key challenge in post-deduplication delta compression is how to find a good reference block for an incoming data block across a wide range of stored data at low cost. Scanning all previously stored blocks is infeasible for sure due to its prohibitive performance overhead. In fact, as explained, deduplication also requires to search for an identical block to an incoming block across the storage system. A common approach for this is to use a strong hash value to generate each data block's fingerprint, which enables a quick exact match search by comparing only fingerprints of data blocks. However, fingerprint is difficult to use for delta compression, as a strong hash function is typically designed to generate significantly different hash values, especially for similar data blocks, in order to minimize the hash collision rate. So to address this, prior work proposes a different approach called data sketching that generates a more approximate signature than fingerprint called sketch, such that two similar blocks have similar sketches. For example, the state-of-the-art techniques, which we call a super-feature-based approach, can generate the same hash values for two data blocks that have a small difference from each other. This enables a quick identification of similar data blocks by comparing over the sketches of data blocks. However, according to our analysis, existing super-feature-based techniques provide a significantly lower data reduction ratio than the optimal. For example, in a general PC usage workload, a super-feature-based approach provides only 60% of the data reduction ratio of the brute force search. It turned out that the core problem is a high false negative ratio. In other words, the super-feature-based approach is very good at generating the same sketch value for highly similar blocks, but it generates different sketches for data blocks that are not that so similar, but can still benefit from delta compression. Next, I will introduce DeepSketch, focusing on its key idea. Our key idea is simple. So we use the learning-to-hash method, a promising machine learning-based approach for the nearest neighbor search problem. Let me briefly explain how a popular learning-to-hash method works for content-based image retrieval. It trains a deep neural network to classify a given image set and uses the last hidden layer to generate a binary hash value of an input image. If two images are similar enough to have the same inference result, it means that the activations in the last hidden layer are also likely to be similar, and so are their hash values. So basically, DeepSketch replaces the existing super-feature-based sketch generator with a DNN-based sketch generator. While the key idea is simple, it was not that straightforward to apply the learning-to-hash method for reference search in delta compression due to the lack of semantic information in our target dataset. To be specific, most prior learn-to-hash approaches deal with specific data types, but in this sketch, it needs to process a general binary data. Therefore, our target data has extremely high dimensional space, so it could be challenging to collect a training data set diverse enough to train DNN with high inference accuracy. So these challenges led us to perform clustering-based DNN training that first clusters an unlabeled data set collected from various real-world workloads and performs supervised learning using the clustering results. So we first cluster similar data blocks in the unlabeled data set and train a DNN to accurately infer a given data block's cluster. Then, using the learn-to-hash method, we can generate similar sketches for similar blocks. The first problem we encountered in this is that existing clustering methods are unsuitable for DeepSketch. For example, k-means clustering requires to properly set the number of clusters, saying the value of k, which is unfortunately unknown in our target dataset. Hierarchical clustering does not have such requirements, but it introduces huge computation and memory overheads for large datasets. So we propose dynamic k-means clustering, in short DK clustering, a version of k-means clustering that dynamically refines the value of k during clustering. The key idea is to iterate 2 steps until the clustering converges. In high level, the first step roughly groups the data groups at low cost while removing low-impact data blocks that have no similar blocks within the dataset. Then the second step finds the best mean block of each cluster and unlabels the outliers that are not similar enough to the cluster's new mean so that it can be clustered again in the next iteration. The second problem we had is the non-uniform distribution of data blocks across the clusters. For example, after DK clustering, in our dataset, the largest 10% clusters contain about 48% of total data blocks, which can make our DNA training significantly biased towards specific data patterns. To address this, we resize every cluster from decay clustering to have the same number of data blocks by either randomly selecting data blocks or adding randomly modified data blocks, depending on the number of blocks in the cluster. After preparing the training data set, we train a DNN as a sketch generator via two-step transfer learning, following the methodology of a state-of-the-art learning-to-hash method called the greedy hash. We first train a classification model that infers a given data blocks cluster and use the learned rated value to train a hash network model that has an additional hidden layer to generate a blocks sketch. Through our hyperparameter exploration, we found a lightweight yet effective DNA model that consists of only 3 convolutional layers and 2 fully connected layers. Next, I will present our key evaluation results. We compared our DeepSketch with 2 baselines. The first one is a simple combination of deduplication and lossless compression, and the other one is Finesse, a state-of-the-art superfeature-based reference search technique for post-deduplication delta compression. We evaluated 11 workloads, 6 workloads that we collected while running different applications on real systems, and 5 workloads collected while storing Stack Overflow database. We used 10% of the 6 traces for training dataset, but did not use the Stack Overflow workloads in our training in order to see the generality of DeepSketch. So this graph shows the average data reduction ratio of Finesse and DeepSketch normalized to the simple combination of deduplication and lossless compression. We observed that DeepSketch provides a large data reduction improvement over the state-of-the-art technique. We also make 2 other interesting observations regarding the Stack Overflow results. First, DeepSketch can provide high benefits even when the workloads are not used in its DNA training, which shows its high generality for unseen workloads. Second, and this is something unexpected, but DeepSketch can significantly improve the data reduction ratio, even for workloads that cannot benefit from Finesse. Next, we evaluated the data reduction ratio when we combine DeepSketch and Finesse and compared the results to the optimal. We normalized all the values in this graph to Finesse. And we observed that the combined technique can provide higher benefits over both standalone techniques, which suggests that DeepSketch and Finesse can actually complement each other. But still, there exists a significant data reduction gap between the combined approach and the optimal, which we believe can be reduced in future work by developing a more accurate DNA model, as done for many other nearest neighbor research problems. As the last main results, this graph compares the right bandwidth of Finesse, DeepSketch, and combined techniques. The results show that actually DeepSketch introduces non-trivial performance overhead over Finesse. This is mainly due to the approximate nearest neighbor search approach that I did not explain in this talk, but we believe this overhead can be also mitigated in future work in various ways, such as hardware acceleration or more efficient data structure. Please see our full paper for more detailed analysis and evaluation. There, we provide an empirical study on superfeature-based reference search, hyperparameter exploration for DeepSketch's DNA, and analysis on performance and space overhead, reference search patterns, and impact of a training dataset. Finally, I'd like to conclude my talk with a quick summary. In this work, we tackle the limited data reduction benefit of existing post-deduplication data compression technique and propose a new machine learning-based reference search technique that can significantly improve the data reduction ratio. We hope that our key ideas inspire many future studies going forward. And thank you for listening to my talk. I'd be happy to take any question from you.